Thank you very much. Again, Professor Shankara Raman, for allowing me to share my research with the ROSE 2024, and my title of the talk is mostly on the work of semiconductor lasers and how we have used these lasers in applications which is ranging from optical comm to millimeter wave and terahertz communication system as well. So I'm Dr. Mohammed Khan, and I'm a senior lecturer in the electronics and electrical discipline at the School of Engineering and Built Environment, Anglia, Ruskin University, Chelmsford, UK. So before starting my talk, just to give a very brief idea about ARU. So, and then I will go to the introduction. So first I will talk about, the light source technology, the broadband light source technology, and how, we can tap on it, and then give some of its applications, and then applications in the millimeter wave infrastructure, and some of our recent work where we have engaged some machine learning techniques as well, and then with the concluding remarks. So let's go to ARU. So Anglia Ruskin University, this was established as a small school of arts in Cambridge in 1858, and then it moved on to expand and become a university, and then renamed as ARU, Anglia Ruskin University, in 2005. And this is where we are situated. And we have different campuses. We have the main campuses in Cambridge, Chelmsford, Peterborough, and Writtle, and our engineering is mostly in the Chelmsford campus. So let's start. Now let me first take you to the broadband light source technology. So when I say broadband light source technology, the first very simple thing that comes in our mind is the light source, which is our incandescent bulb or our CFL lamps. So this is a sort of emission spectrum that you see from incandescent lamp, which says which has wavelengths incorporating from 400 nanometers up to near infrared 16 to 1700 nanometers. Now, besides this, in the last few years, there are a lot of research that has been done where so semiconductor devices has been used in order to say realize such kind of broadband light source technology. So the first thing is the superluminescent diode, as you can see, and the laser diodes. So these are some of the representation of the wavelength coverage that you get when you use multiple superluminescent diodes. And these are the laser diode results, which I have put on this figure, and this is based on the last 15-20 years of research. So as you can see, our laser diodes, yes, its emission spectrum is narrow, but it has a high power. On the other hand, our incandescent bulb and our SLDs, the emission wavelength is broad, but the power is less. Now, why we are moving towards these kind of technologies? So my focus of my talk will be mostly on the broadband semiconductor lasers. So therefore, here what we are doing is, rather than trying to generate a very narrow peak, a sort of almost single wavelength light emission, which is typical of our lasers definition says, or I would say how people will visualize when the word laser comes to them, right? So you have just very narrow a single wavelength. But this is a type of technology where we are doing the otherwise. So rather than a very narrow, emission spectrum, we have quite a broad range of emission spectrum. So why we are moving towards these broadband sources, so what are the application of these kind of sources, so there are several multidisciplinary field applications. So I have put forward a few of them. So as I told you, rather than going for conventional semiconductor laser, which they are narrow band, we are moving towards the ultra broadband semiconductor lasers. And right now we are focusing in this region, which is in the near infrared region of our emission spectrum, around 1.3 to 1.5 or 1.6 nanometer. And the applications, as you can see, telecommunications, medical diagnostic, gas sensing, imaging, metrology, and even in the LiDAR and the fiber gyroscopes. So in all these places, you find the applications of broadband laser diodes. And in specifically in optical applications, where my focus is, so we can generate tunable lasers, we can generate multi-wavelength lasers, we can have a broadband detector, and not only that, we can have some sort of ultra short pulse generation, like in optical clocking application. So this is an example where, a broadband laser, so if you see here, this magenta, this is like the lasing output, how, slices of this can be used, and then it can be tuned to get multiple wavelengths, or a multi-wavelength laser. So where all these different slices can be used simultaneously, either directly or through an arrow waveguide. So this is an arrow waveguide, which again takes the slices of these emission spectrum, and that can be individually used. And last but not the least, the optical clocking application, where you can have a very ultra short pulse generation, because we know it very well that in the frequency domain, if the emission bandwidth is large, then in the time domain, the pulse width will be very small. So we can get a pulse width in picoseconds and in sub-picoseconds as well. So the main motivation of going for broadband, laser diodes in optical communication, I will not spend much time on this slide, because we all know very well, how the global mobile and data traffic is booming, and therefore our infrastructure, which is already in place, our optical communication infrastructure, has to cater these demands. Okay, and the forecast is really, very high. So we need to cope up with the these kind of demands. So what kind of alterations, or what kind of alternate solutions that we can get in order to meet these demands? So for example, how the data traffic is expected to grow, and then how the total number of subscriptions are expected to grow. So in a nutshell, you are looking for a very high data traffic, okay, very high bandwidth, but at the same time, we do our best to use our existing infrastructure, or slight modifications to the existing infrastructures. So, what can be done? So this is the motivation why we want to bring these kind of broadband lasers in optical comm. Okay, so here I'm now giving you an example of how the BLDs, which is our broadband laser diodes, can help in say passive optical networks. So as a source, as a light source. So it can help in reducing the operational and the capital expenditure. That means you can have just a unified transmitter for several say users. So therefore it can help in mass deployment. Then how we can increase the bandwidth, we can try to go beyond C, which is the case now. Everybody is now going for ultra wide bandwidth, which covers, SC, LU, all these bands. That is, it is going, on the longer wavelengths, which is more than, 1575 nanometers, going for 1600, 1625, 1650 nanometers, and also the shorter wavelengths, which is 1475, 1450 nanometers as well. So we are trying to increase the usage of our bandwidth to cater, more number of subscribers, and also to increase the complete throughput. Then we also want our passive optical networks, to be flexible and scalable, because these are some of the requirements what people are envisioning for our next generation passive optical networks. So flexible and scalable. So here, we can go with sort of a free space optical communications, which is now, has been a point of active research, from the last 10, 15 years. Then we go for hybrid fiber FSO, or we can go for hybrid optical as well as radio networks, which is nothing but radio over fiber technology. So these are what, we can achieve, some of them using the broadband laser diode, which is the first and the second requirements. A unified transmitter, and then we can also get a unified receiver. And here I'm just showing you about, in the computer communications as well, because this is what I have just now talked about in optical communication. But in the computer communication, that means when we go and, go for, a device level or a chip level type of communication, then still we can have broadband laser diodes, giving, so many carrier signals. As you can see here, this is a simple, say a representation of a wavelength division multiplexed system, where what we do is we select, different wavelengths, and each wavelength corresponds to a user, and the user is going to use that carrier frequency for communication purpose, whether it is bidirectional or unidirectional. So from red to, violet, this is what it is representing. So here, for example, now here you're using more than 10 different wavelengths for like 10 users. So a broadband laser diode technology, how it can address this. So rather than using individual lasers, a narrow line width individual lasers, we can go with a broadband laser and then just take a slice of it. And one slice, that means one particular wavelength, can serve as a carrier for one particular channel of your WDM system. And then you can have the second slice as the second wavelength, and so on. So this is how, the broadband laser diodes can help. That means all these carrier frequencies or the carrier wavelengths, which is generated by individual lasers. So for example, if you have a 20-channel WDM system, that means we have 20 different lasers. So rather than we have 20 different lasers, we can try and get all these 20 different carrier frequencies with a single broadband laser diode. So even in the computer communications, the broadband laser diode can serve as an optical source or an optical transmitter source. And not only that, so we also want, our, data center to be tidy, right? So, here also, broadband laser diodes can serve in minimizing, say first thing is minimizing the number of optical sources that are used, and then second is if we use, the free space technology, that is free space optical communication, then probably, these fibers that we see, which is running around the data centers, can also be reduced. So as I have told you, that this is the typical, say block diagram of a WDM system. And these are the typical, say emission spectrums of a laser. So this is a emission spectrum of a DFB laser, which is, as you can see, it's a sharp, almost a single wavelength type of emission spectrum. And this is the Fabry Perot laser, where we do not use the gratings. We do not exploit the gratings. We just exploit a Fabry Perot cavity, and we will get this kind of emission. So where each of these lines is a longitudinal mode, but still it is narrow. It is considered narrow. And on the other hand, this is how the emission spectrum of a broadband laser diode looks like. So it can cover a very, broad, emission bandwidth. A 3 dB bandwidth can go up to, say 50 nanometers or even more than 50 nanometers. So as I have explained it to you, the main objective is, rather than having this WDM system, which is a typical WDM system where you have, individual laser diodes generating individual, wavelengths or carrier frequencies, which are multiplexed and then demultiplexed. So can we replace this many diodes? If it is an N-channel WDM system, then it is N wavelengths and N laser diodes. So can we replace it with a single broadband laser diode, which can give you all these, carrier wavelengths or all these carrier frequencies? So if this can be done, then this can address the issues of energy efficient communication, which is the green communication, and it will also help in, say reducing the cost as well. So this is where, we are trying we are trying to demonstrate the usage of the broadband laser diode technology. And now let me take to you, slowly from the material level, then I will take you to the device level, just to give you an overview of, how these, laser diodes are giving us a very broadband emission, and then to the application side. So we will take to the material level. So these broadband laser diode technology is coming from semiconductor nanostructures, and we know it very well about quantum wells. We know it very well about, say quantum dots. So these have been, in the research field from the last more than 20 years now. And we have also got another nanostructure, which is called as quantum wires. So these kind of wires are considered, to be somewhere between the wells and the dots. That means it's elongated. So dots have a 3D confinement, whereas quantum wires will have 2D confinement. Whereas in one dimension, it will not be confined. That means our electron energy states will not be confined. So, in a way, theoretically, it has been shown that if you go for a quantum dot, then the gain spectrum that your material can give, the material gain can be very narrow. That means your energy states, your transition energy states are really very specific, and that's why you are getting a very high gain compared to wires and compared to, bulk and the quantum wells. And the quantum wire is also somewhere here. So now what we have done is, this terminology, which is called as quantum dash, has been, say given again around 10-15 years ago. So this is the nanostructures which are, a mix of dots as well as wires. Okay, so if you see, so these are the wires, are very long elongated ones, but these quantum dots, they are, 3D confined. But quantum dashes are those nanostructures which have, the behavior, or which have, both dots and wires together. So if you can see here, some of them are like dot, and some of them are like wires. And this has to do exclusively, from the material growth point of view, because if we try to grow say quantum dots on indium phosphide substrate, because indium phosphide is the technology that allows us to go to these emission wavelengths of our C band and L band. So instead of quantum dots, you see such type of growth, which is dots and dashes, because mostly these are self-assembled growth. That means these are random, growth. So not much, controlled. But now, we have a much controlled, say, technology already in place. People from Germany, they have already shown a very nice quantum dots on indium phosphide as well. But typically, when you try to grow, then this is what you get on indium phosphide. Until then, unless you go and do some specific steps in order to just grow quantum dots. So typically, you get quantum dots and quantum caches. So very random. So this is the randomness that we try to exploit. So what we do is the size of these quantum dots and quantum dashes, specifically, the height. So that is the major player in deciding the emission wavelength. And as you can see, it is highly tunable. That means it can go from 1.2 to 1.6, 1.7 nanometers. So this is one thing. And the second thing is, it is highly inhomogeneous. Highly inhomogeneous means that the size distribution of dots and the size distribution of dashes are really, very, inhomogeneous, very random. So that is the range of, say the height. If we try to measure, then this range is very high. So the variance is quite high. So if you want to put it in a figure format, then it's something like this. So that means your energy states, because as the size changes, so the size dictates the transition energy states of the quantum dots and the quantum wells. That means the energy states of the quantum dots, so the energy transition levels of the quantum dots and the quantum wells changes. That means it is now dispersed. So this is what we are trying to show here, that now the energy states are no longer, narrow. This is the case when you have, the quantum dots or the quantum dashes, which are, or the quantum wires, I would say, which are really, of almost similar size. Then you have a very narrow gain emission. But if it is very random, then you will have a very broad, say, gain emission, because of dispersive energy states. So this is what we exploited, and then we made our devices. So you can see, these are the quantum dots. So it is an indium arsenide quantum dots, which are grown on indium phosphide substrate. So this is an AFM image. These are the SEM, the TEM images, and this is just a pictorial representation of how they looks like. And then, we built, say an epitaxy with, P and the N layers over the active layer. And then, when we fabricated lasers and we tested the lasers, this is what, we got. So because your gain is gain emission bandwidth, your gain bandwidth is very broad. That's why, these are the solutions of your Fabry-Perot modes, because we are looking for a Fabry-Perot laser. That means, you have two mirror ends. One end is here and one end is here, and this forms the cavity. And this is your epitaxy, and this is your laser bar, which have been fabricated. And these are the solutions of your Fabry-Perot modes, and those which satisfies, the emission bandwidth, say loss, then those are the one which will be available, and then they will satisfy the lasing conditions. And this is what you're seeing here. So these are all the Fabry Perot modes for the quantum dash type of laser diode. So the emission bandwidth is like 50 nanometers, and it is covering, 1.5, 1.6 nanometers, 1.65 as well. So these are the material system that we have used in order to demonstrate such kind of broad emission. And not only, our group, there are several groups who are working in this quantum dash technology. So, these are some of the results. In fact, this is a very active group from France, CNRS France. They were very active, and even now they are active. So they actually used these broadband laser diodes to show the ultra short, say, pulse generation. So if you see here, they showed a pulse generation of sub picoseconds, which is 560 femtoseconds and 870 femtoseconds from a broadband laser diode of quantum dash, whose cavity length, that is 170 micrometer and 120 micrometer. Cavity length is, this is the cavity length because this is the Fabry Perot mirrors. So they demonstrated this. And, getting grazing from such a small cavity itself, is saying that, the quantum dashes is a high gain material. Otherwise, overcoming the cavity loss from such a small cavity is quite, you require a lot of, say, photon generation to compensate for that. But still, it is able to compensate, and it is able to raise, is demonstrating the high material gain of the quantum dashes. Not only that, we also looked at the electroabsorption and the electro-optic characteristics of quantum dashes. Again, with the aim of trying to see whether these broad band active regions can they be used for modulation purpose. And so these are some of the results that we have seen, and we compared it with the quantum dot and as well as with quantum well structures. So as you can see, the results of our quantum dash, it falls between the quantum dots and the quantum wells, because we know very well quantum wells are really excellent to realize say electroabsorption modulators, are very say high extinction ratios and very strong change in the refractive index if you want to use it as an electro-optic modulator. But for quantum dots, we have seen that it is not that good. However, because quantum dash, it is somewhere between the characteristics of quantum dot and quantum wells, it has some reasonably good characteristics. So that's why we strongly believe that this can say work as a good electroabsorption modulator as well. So that means you can have a very broad band modulator. So it can cover all these wavelengths. If you can see here, so it can modulate a light from 1460 to 1650 15 nanometer. So this was the electroabsorption and the electro-optics characteristics of that broadband gain medium. So now let me take to the deployment. So that now these devices, how these devices have been performing at the application level, and how are the results. So if you can see here, as I told you, there are 2 to 3 groups who were really very active in using quantum dash lasers in optical communications. So I'm just showing you, some 3 to 4 years old result. So this is again, if I'm not mistaken, from the CNRS France group. So what they did is they have used a single quantum dash laser, and their quantum dash laser is emitting in the C band. For example, if you see here, this is their emission bandwidth, and they have taken around 32 channels. That means, they were taking around, say 32 longitudinal Fabry periods modes. Okay, 32. So out of 38, they used 32 for demonstration of the communication. So this is a very, it's a broadband laser, a single one, as you can see. And then, you separated each of them. Not each of them, I think the even and the odd modes, because this is for the optical communication purpose. And then they modulated 32 of them with 40 gigabaud, which is 160 bits per second, the QAM modulation, 16 QAM, and they transmitted it over 75 kilometer of single mode fiber. And they used the dual polarization scheme, and they demonstrated 6.7 bits per second per hertz spectral efficiency. So this is with a single device. So single device, and then showing 32 channel WDM system. That means these 32 carriers are being, say, generated from a single device. And then, this was improved further to 12 terabits per second. So this is the total capacity of the system, which is 12 terabits per second, from 10.68 to 12 terabits per second transmission capacity in C-band, where here they were. So what they did here is, they used 32 channels, and these 32 channels, they modulated it with 40 gigabaud. Okay, and then transmitted it over 75 kilometers single mode fiber. So they separated the even and the odd modes, and then they modulated them. So they refined this in their next work. So in their next work, this is their next work, where they refined it. They have taken now the 60 channels, and what they have done is they have transmitted say 32 QAM signal, which is like 80 gigabits per second over the 75 kilometer single mode fiber, and then they were able to say demodulate them, and this corresponds to a total 12 terabits per second transmission capacity. So this is okay. Let me go back. Let me go to the next slide. Okay, so this is our the C band. So now, as I told you, these quantum dash lasers can be used, can be tuned to L band. So this is the work of L band, where say out of these 5 different channels or 5 different modes, 3 modes were used, and a communication over these 3 modes were done in a very similar way, where the odd lines or the odd Fabry period modes were separated, and the even Fabry periods modes were separated, and then they were transmitted to a different length fiber, just to say decorrelate them, and then transmitted over 10 kilometer fiber, and then the demodulation has been done. So here I just wanted to stress out that in the L band, we do not have say equipments that can amplify the signals. So therefore, we had very limited power to do that. This is one thing, and the second thing is, these quantum dash lasers in the L band, they were not highly, say frequency and the mode locked. We did not observe that in L band. So whereas in C band, the self mode locking, concept, the self mode locking was seen, and that actually helped in, say, doing the modulation, especially the phase modulations on those channels or those, say, carriers. So this is the L band work for only 3 channels. Then some other say works. So where say tunable lasers were also shown. So if you see here, you can have, a single mode which is emitting from your, say, multiple wavelength emission. So one mode, or, you can have, say 3 or 4 modes, or even, 16 modes. So here, the concept of what we say it as self-injection locking has been used. So this is a technique, where what we do is part of the optical power of our laser is fed back towards the laser itself, and in order to lock a particular wavelength. So this actually, significantly improves the phase noise of the signal, as well as it helps in reducing the relative intensity noise of the signal of the carrier, and that actually helps in improving the modulation capability. So these are some of the results. So what we did is we tuned this mode, from around 1600 nanometers to 1610 or 1615 nanometers. So we tuned, and then we demonstrated, the communication over each of these modes. So this is a sort of a demonstration of a tunable laser in optical telecommunications. So this is again the extension of that work. So where 11 nanometers tunability was shown. So let's now I will now move to say how these kind of broadband lasers can be used in radio over fiber, especially addressing the millimeter waves. So okay, so the millimeter waves. So the main idea about the millimeter waves, that photonic signals can be used to generate millimeter waves, and the idea is, if you can select two optical modes, or two say optical wavelengths, and beat it across a photodiode, then the difference between these two optical modes, if you select it to be in the millimeter wave region, then the output of your photodiode, which is just a square law detector, will be your millimeter wave signal in the RF domain. So this is the idea. So people have used this idea to generate 25 gigahertz millimeter wave signals. So where they used dual wavelength DFB lasers. So if you can see here, you have two wavelengths, and the difference between these two wavelengths is set to be 25 gigahertz in order to generate the 25 gigahertz millimeter wave signal. So the photonics equivalent of your millimeter wave signal is passed through a single mode fiber, and only towards the end it is now converted from the optical domain to the RF domain, and then passed through these horn antennas and then detected. So this is a demonstration of 25 gigahertz using 12 wavelength DFB lasers. So in a similar way, people have used, broadband quantum dash lasers as well. So as you can see, so from these, very broadband emission, only two particular, say adjacent wavelength, two modes has been used for the demonstration of 28 gigahertz millimeter wave signal. And this is another one. So where a dual wavelength DFB laser is used. So let me take here. So here 65 gigahertz millimeter wave is used. So here the difference between the Fabry-Perot mode plays the most important role. So that means you have to design your Fabry-Perot cavity in such a way to get a millimeter wave frequency, between two adjacent Fabry-Perot modes to be equal to the desired one. And the same thing has been used, the similar idea has been used in L-band as well. So in L-band, we were able to select two modes, and then we were able to modulate one of the mode and then transmit over the single mode fiber, then the free space, and then the wireless channel. So where we were able to show, say, 28 and 30 gigahertz millimeter wave signals, and even the bidirectional 25 and 28 gigahertz millimeter wave signals. And recently we even went to 100 gigahertz sub-terahertz signal also. So as you can see, we were able to select these two modes. So I think these were our very recent results, where we started using say machine learning, and we were trying to generate the orbital angular momentum modes in 1.6 micron wavelength using quantum dash lasers and trying to detect it. So this is our very latest results, and it is still going on. So I think to conclude, so this is the broadband laser diode technology which I have presented. So this time, this indium arsenide, indium phosphide technology, so I have explained it to you, how this active region can be used in order to realize broadband laser diodes, and how these broadband laser diodes can be used in the optical communication, and the performance of the quantum dash broadband lasers, how they can be used in millimeter waves and the sub-terahertz infrastructure. I think that's it. So thank you very much, Professor Shankara Raman.